Today's lecture on maxima and minima is very important. In fact, in this lecture, we will learn about the first derivative test for maxima and minima of a function. That is, we will be able to know after this lecture that how we can test by finding the first derivative of the given function, that when the function is maximum or when it is minimum, and what are its maximum and minimum values. Actually, this first derivative test is also known as sign scheme. Actually, by knowing the sign of the value of the first order derivative of the given function, we can decide when our function has maximum value and when it has minimum value. We will also learn that when the function is neither maximum nor minimum. Okay, so let us see what are the rules for finding the maximum or minimum value. When you say maximum and minimum, you can use the term extrema. When you say extrema, that means both minima and maxima. Okay, so if you consider a function, let us say y equal to fx, and you have to test with the aid of first derivative test that when this function will be maximum or minimum, then how we can decide it. Actually, the step which must be followed for solving such type of problems, let us see what are those steps. First of all, you have to find the derivative of the given function. It means we will find dy by dx, which is denoted by the symbol f dash of x. Actually, this derivative is defined only when the function is continuous. But you will see later on that this idea can be used in case of the discontinuous function too. But here I am just talking about the continuous function whose derivative is defined at each and every point. So what we will do? In first step, we will find the derivative of the function, that is f dash of x. Okay. Now in second step, we find the critical point of the function y equal to f of x. And you have learnt about a critical point of a function in the previous lecture. When the function is continuous and you have to know the critical point of that very function, what you do? Actually, we simply equate the derivative of the function to 0. It means we will write f dash of x equal to 0 and then solve the equation. And after solving the equation, we find the value of x. The value obtained after solving f dash of x equal to 0 is denoted by the symbol, let us say x naught, and this is called critical point. This x naught may have one value or it may have more than one value. So there may be one or more than one critical points of the given function. Once you find the critical point after equating f dash of x equal to 0, now by the sign convention of the derivative f dash of x, we can decide that at x equal to x naught, our function is either maximum or minimum, or it is neither maximum or minimum. Okay, this is actually done by the sign scheme. Let us see this figure. I am talking about here the maximum value of the function. As you can see, I have plotted a graph here which is of the function y equal to f of x. This is just an arbitrary curve. Okay, and it is clear from this graph that corresponding to this point P, the function has a local maximum value. Okay, it is clear. And so corresponding to this point P, x will have a value x naught, which is called critical point. But when f dash of x is equal to 0, then the function may be maximum or minimum. Both are possible. So how we can decide that at this x equal to x naught, the function is either maximum or minimum? Because this condition holds for both maxima and minima. Whenever the function f of x is maximum, f dash of x will be equal to 0. And if it is minimum, even then f dash of x equal to 0. So how we can decide that when f dash of x equal to 0, the function is maximum or minimum? And for this, you have to see this curve. Let us see here. When x is less than x naught, in this region, for this part of the curve, let us say AP, for AP part of the curve, x is less than x naught. You can see. And when you will find the slope, that is f dash of x, corresponding to any point on this curve for x less than x naught, what you will get? Let us see. I am just finding the slope of a point, let us say here, which is actually, let us say C. And you can see that this slope, if this angle is psi, then slope of this curve corresponding to this point this point C, where x is less than x naught, that will slope, if we denote it by m, that will be tan psi. And this tan psi is simply equal to f dash of x. Okay? And as you can see, psi is less than 90 degree, so this slope will be greater than 0, that is positive. Okay? But when you talk about a point in another side of the curve, let us say for the part BP of the curve, okay, where x is greater than x naught, x is greater than x naught, okay, and you try to find slope of this curve corresponding to a point for which x is greater than x naught. For that, we will again draw a tangent, and you can see this tangent will make an angle phi with the positive x-axis, and as phi will be greater than 90 degree, so this tan phi will be less than 0, that is negative. So from this curve, you can construct a rule that this point will have a local maximum value of the function f of x. So rule is simple. If you can see at x equal to x naught, the f dash of x naught is 0, and if for x less than x naught, f dash of x is positive, okay, and when we cross through this point x naught and goes in the region where x is greater than x naught, and then f dash f of x becomes less than 0, that is negative, then you can say that at this point x equal to x naught, our function has maximum value. So the rule is simple. It means corresponding to the critical point x equal to x naught, the function will have maximum value only when the sign of f dash of x changes from positive to negative. Positive to negative. You can see the sign of f dash of x changes from positive to negative. Then we say that at this point x equal to x naught, our function has maximum value. I think we have understand how we can decide that at the point, at critical point, function is either maximum or minimum. You have learned only about about maximum. Now the sign scheme for the minimum value of function at x equal to x naught will be just reverse, and so you can see here. Now in this figure I have shown the graphical plot of a discontinuous function. You can see that this function f of x is actually discontinuous at this point P, and the function has a maximum value. Again you can see as the function is discontinuous at point P, so we cannot define the finite value of f dash of x naught. It means derivative of this function at corresponding to this point P is undefined, because you know corresponding to this point P there will be two values of slopes. First one, if you want to find the slope considering this part of the curve, then the slope will be positive, and when you will find the slope of this curve corresponding to point P, considering the another part of the curve, the slope will be negative. But for a continuous function, the slope will have only one value corresponding to a particular point. So we simply say that as the function is discontinuous at point P, so derivative of this function cannot be defined at the point of discontinuity. But again see that when we will find the slope of the curve corresponding to any point in this region where x is less than x naught, then you can draw a tangent and you can see that this tangent will again make an acute angle which is less than 90 degree, and so the slope will be positive. Okay, so I have written here that f dash of x is greater than 0. But corresponding to a point in the region where x is greater than x naught, you can see that when we will draw a tangent, this tangent will make an angle phi which is greater than 90 degree. Okay, and so the slope will be negative. So again you can say in case of discontinuous function 2, when the sign of f dash of x changes from positive to negative on passing through the point x equal to x naught, then this point x equal to x naught corresponds to the maximum value of the function. Okay, so this idea of sign scheme is valid in both cases, that is in case of continuous function and in case of discontinuous function. But in case of discontinuous function, you can't write that f dash of x naught is equal to 0. You cannot write this because f dash of x naught is not defined in case of discontinuous function. And you have learned that at the critical point, either f dash of x equal to 0 in case of continuous function, but in case of discontinuous function, f dash of x at the critical point is not defined. Okay, so I hope you have understand. Now, similar situation is for the condition of minima, and all the conditions will be just reversed. And for knowing the idea of minima by the first derivative test, let us see this figure. I have again plotted a function y equal to f of x here. And as it is evident from this figure that corresponding to this point P, for which x is equal to x naught, the function has a local minimum value. And you can check that when we talk about the region where x is less than x naught, in this region, and we consider any point, let us say A on the curve, and we find the slope of the curve corresponding to this point, then you have to draw a tangent, okay, at this point A, and you can see that this tangent makes an angle psi with positive x-axis which is greater than pi by 2. And so you can say that in the region where x is less than x naught, their slope of the curve is negative. So I have written here that f dash of x is less than 0. That is negative. Okay. And you can also see in this second figure that in the region x less than x naught, f dash of x is less than 0. That is negative. But when you will see another point, let us say point B in the region where x is greater than x naught, and again you try to find the slope of the curve corresponding to this point P where x is greater than x naught, then you can see that this tangent will make an angle phi with the positive x-axis which is less than pi by 2. And if it is less than pi by 2, slope will be positive. And so you can say that when the sign of the first order derivative f dash of x changes from negative to positive when we pass through the point x equal to x naught, then corresponding to this point x equal to x naught, our function has minimum value. So this point corresponds to the local minimum of the function f of x. Okay? And this figure is actually for a continuous function. The same situation will be in case of a discontinuous function. And you can see this figure, this is actually a graphical plot of a discontinuous function. At this point P, again you can see corresponding to this first part of the curve, slope will be different from the slope for the second part. So you can say that our function is discontinuous at this point P. Okay? And as it is discontinuous at point P, so we cannot define the first order derivative of this function corresponding to this point P. So I have written here that f dash of x naught is not defined. Okay? But again you can see for this region where x is less than x naught, you can see that the slope of the curve corresponding to any point x less than x naught, that will be negative, because when you will draw a tangent to this curve at any point x less than x naught, then the angle made by this tangent will be greater than 90 degree. Okay? And so slope will be negative. So I have written here that f dash of x is less than 0. But if you consider any point on this second part of the curve and draw a tangent to the curve corresponding to that point, you can see that that tangent will make an angle phi which is less than pi by 2, and so in this region the slope of the curve or f dash of x will be positive, that is greater than 0. So again you can see that a function will have a minimum value at this point x equal to x naught even when the function is discontinuous, when f dash of x is negative or less than 0 for x less than x naught, and this f dash of x is positive in the region where x is greater than x naught. So in this way you can find the value of f dash x, and by checking the sign of f dash x you can find out that the function is either maximum at x equal to x naught or it is minimum. Okay? But sometimes there are some functions in case of which there will be no change in sign when we will pass through a point x equal to x naught. As you can see this figure, here you can see that when we pass through the region x less than x naught to the region where x is greater than x naught. In fact, in both sides you can see that the slope of the curve is positive, because when you will draw a tangent, the angle made by the tangent will be less than pi by 2 with the positive x-axis. And you can also see here when we will draw a tangent, this tangent will make an angle phi which is also less than pi by 2. So slope of this curve after passing through this point P does not change its sign. It means f dash of x in both sides of this point P are positive. In other situation this may be negative too. It means in both sides the value of f dash x will be negative 2. So you can say that at this point P, this function is neither maximum nor minimum. Okay? In fact, in this condition we simply say that the value of our function is constant, stationary. So this is actually the condition for a stationary function. So you can say that this f dash of x will be equal to 0 in three conditions. F dash of x will be 0 when fx is maximum, when fx is minimum, and when fx is stationary. Okay. In all these three conditions, this first order derivative of our function is equal to 0. Actually, this fact is vividly used when you study the different topics of physics. Okay. Now, I have shown the same fact in case of this discontinuous function. This is actually the case of discontinuous function. And here you can again see that the sign of f dash of x does not change when we pass through this point P, corresponding to which x is equal to x naught. As you can see, in this region where x is actually less than x naught, you can see that f dash of x will be negative, because again when you will draw, I have drawn the tangent several times so you can understand it. When you will draw a tangent at, let us say, this point, that tangent will again make an obtuse angle. It means angle greater than 90 degree, and so the slope will be negative, or f dash of x will be negative. And again in this second region where x is greater than x naught, you can see the shape of the curve, that again for this part of curve f dash of x, that is slope of the curve, will be negative. So you can see on passing through this point x equal to x naught, the sign of f dash of x does not change. It remains negative. It is negative in both sides, that is in the region x less than x naught and x greater than x naught. So at this point f x equal to x naught, in this case f of x naught is not defined. It is not defined, okay, because the function is discontinuous at this point. But in this region where x is less than x naught, you can see this figure that this f dash of x is negative. And again in this region where x is greater than x naught, this first order derivative f dash x is again negative. So you can say that our function, the first order derivative of our function does not change its sign when we pass through the point P. And so the point P will be the critical point where its derivative is not defined, and this function is neither maximum at this point P nor minimum. Okay, neither maximum nor minimum. So these were the first order derivative test, how you can find that if given function is either maximum or minimum or stationary. Now what you have learnt, that will be actually I am just going to explain by taking some illustrative example, because you know in mathematics whenever you solve some numerical problems, then your concept becomes crystal clear. Only knowing theory, everything is not known to you, but after solving the problem you get the each and every aspect, each and every concept of the theory. Okay, so let us take some illustrative examples here to clarify our concept. In the first example, the problem is if f of x is equal to ax cube plus bx squared plus x plus 1, you can see here, has a local maximum value of 3 at x equal to minus 2, then find the value of a and b. This question has been asked in IIT JAM exam for computer application 2010. So this is a very important problem. Actually in this condition, in this question, not condition, it is given that our function has maximum value which is equal to 3. you have not to find what is its maximum value, but it is given in this problem that the function has a local maximum value of 3, and critical point is also given in this problem. It means the function has maximum value equal to 3 when x is equal to -2. These two conditions are given, and then you have to evaluate the value of the unknown constants a and b. So here it is known that the maximum value of the function is 3, and it is also known at which point this function has maximum value. The point, that is the critical point, where the function has maximum value 3, that is x equal to -2. So this x equal to -2 is x naught. Okay. So it is a very simple problem, and you can easily solve this problem. As two quantities are here evaluated, so two conditions are given in this problem. You can see the given function, you can see, is this much: f of x equal to ax cube plus bx square plus x plus 1. Okay. Now, according to our problem, the given function f of x is maximum, that is f of x is equal to f max, and that is equal to 3. But where it is equal to 3? It is it is maximum, and its maximum value is 3 at point x equal to -2. So this x equal to -2 is the critical point of this function. So when you will substitute x equal to -3 in this equation 1, then you will get the maximum value of this function, because the problem says that the function is maximum when x is equal to -2, and its maximum value is 3. So let us put x equal to -2 in this equation 1, and then you will get the maximum value of function f of x, which is 3. So f of -2, it is given that it is equal to 3, and that will be equal to what? We will simply put -2 at places of x. So this will be a times -2 cube plus b times -2 square minus 2, because there is only x, and plus 1. And so 3 will be equal to -8 plus 4b minus 1. Okay. And when you will take this -1 in LHS, this will become 4. So 4 is equal to -8 plus 4b. Now let us take 4 as a common factor, and that will cancel out, and your equation will be -2a plus b equal to 1. Now we have one equation containing a and b. So if there will be another equation containing a and b, then solution will be possible to evaluate the value of a and b. Now let us see that x is equal to -2 when the function is maximum. But we know that when function will be maximum, then actually this f of x, when the function will be maximum, then then f dash of x will be 0. So we can write that f dash of x when x equal to -2, that is equal to 0. Okay. Now let us differentiate the given function. This is your given function, and we will differentiate it. So after differentiating, you will get 3ax square plus 2bx plus 1 when x is equal to -2, and that will be equal to, in fact, 0. Now we know that when x is -2, then f dash of x is 0. Okay. So now we will put x equal to -2. So at the place of this x and this x, we will simply put -2. So this will be 3a times -2 square plus 2b times -2 plus 1 equal to 0. And after simplification, we will get 12a minus 4b plus 1 equal to 0. Okay. And so you can write 12a minus 4b equal to -1. And now you can take 4 as a common factor, and this equation will become 3a minus b equal to -1 by 4. Okay. Now we have two equations. This equation you can see is 3, and this equation 2. So when we will simply add these two equations. This b will cancel out and you will get that a is equal to 1 minus 1 by 4, which is 3 by 4. So in this way you have obtained the value of a. Now let us put this value of a, which is 3 by 4, in this equation number 2, this equation 2, and substituting this value we will get minus 2 into 3 by 4 plus b equal to 1, and so b will be equal to 5 by 2. So in this way we have calculated the value of a and b. A is equal to 3 by 4 and b equal to 5 by 2. So you can see how easily we can solve this type of problem. Okay. Now I am just going to solve another problem, and after this solution your concept will be very clear regarding the first derivative test. The second problem says that find the points of local maximum or local minimum corresponding to the maximum and minimum values of the function f of x equal to this much. Okay. Actually in this problem we have to find when our function will be maximum, when our function will be minimum, and we have also to find the maximum and minimum value of that function. Okay. And so definitely we have to see about the sign scheme in this problem. You can see I have written here the given function, which is f of x equal to this much. Now you know when our function is either maximum or minimum, then its first order derivative will be 0. So as our function is either maximum or minimum, we can write f dash of x equal to 0. And this is your function. And when you will differentiate it, this will be 6x square minus 42x plus 36 equal to 0. You can take this 6 as a common factor. So this will be 6 times x square minus 7x plus 6 equal to 0. And as 6 is not 0, so you can write x square minus 7x plus 6 equal to 0. Now when we will factorize it, you can write x square minus 6x minus x plus 6 equal to 0. And so in this way you can see that you will get x equal to 1 and x equal to 6. So there are two critical points. X naught is here, 1 and 6. These are the critical points. Now we have to test that when x is equal to 1, then our function is maximum or minimum. And when x is equal to 6, then our function is maximum or minimum. This we have to test. And for this we will actually see the sign scheme. You can see when you will find the value of f dash of x for a value of x which is less than 1. Let us say f dash of 1 by 2. What will be this? You can see f dash of x is equal to this much. So let us say this is our equation. F dash of x, I am writing here, this is actually equal to 6x square minus 42x plus 36. This is the value of f dash of x. Now substituting for x a value less than 1. Let us say for example f dash 1 by 2 we have to evaluate. I am not evaluating it, but you can check. When you will substitute 1 by 2 at the place of x in this equation 2, you will definitely see that this will be positive. It means greater than 0. And now let us put the value of x which is greater than 1 but less than 6. Let us say for example we put x equal to 2 in this equation 2. I am not doing the algebra, you can do it, and then you will see that this value will be negative. So you can say that on passing through this point x equal to 1, the sign of f dash of x becomes positive to negative. And you have learnt that when the sign of f dash of x changes from positive to negative, then at x equal to x naught our function is maximum. So corresponding to this point x equal to 1, this function will have maximum value. Okay. And so if you want to find the maximum value of the function, you have to put x equal to 1 in the given expression of the function. So let us put x equal to 1 in this equation 1, and then you will get its maximum value, which is equal to -3. Okay. Now let us check the sign of the function f dash of x when x is greater than 6. You have learnt that when x will lie between 1 and 6, then the function f dash of x is negative. You have already done it here. Now when you will substitute x greater than 6, for example, let us put x equal to 7 in this expression, equation 2. I am again not doing the algebra. You can do it. When you will put x equal to 7, you will get that this f dash 7 is equal to positive. You will get positive value. So you can say on passing through this point 6, the sign of f dash of x changes from negative to positive. And we have learnt that if f dash of x changes its sign from negative to positive, then at x equal to x naught, our function has minimum value. So corresponding to this point x equal to 6, function f of x is minimum. And now if you want to find the minimum value of this function, you have to put x equal to 6 in this equation 1. Okay. So I have substituted here x equal to 6, you can see, and then our result is -128. So the maximum value of this function is -3, and its minimum value is -128. I hope after the solution of this very important example, definitely you have learned how we can decide that our function has a maximum value or minimum value at a given value of x. Okay. So watch this video seriously and note down these facts in your notebook and revise it. Definitely everything will be clear to you. Okay. Thank you very much.